Alright guys, so this is Axel, and today we're going to be going over my first of many videos on Lagrangian mechanics. And if you don't know what Lagrangian mechanics is, then don't worry, because this course is going to start from the very basics. So this is my introduction video to basically let you know what you need to know in order to actually understand what's going on. In this video, we're going to talk about the motivation behind the Lagrangian, so forces versus energy, why we need the Lagrangian, and why the Lagrangian is more useful in some situations than others. I'll also talk about the mathematics and physics required to do the course. So first, Newton formulated physics using vectors and forces, now known as Newtonian mechanics. And so for Newtonian mechanics, he's using vectors, free body diagrams to analyze physical systems, and it gets extremely messy. Because if you have multiple particles, each one has 3 different coordinates. You have to analyze all the coordinates, and if you have, say, 1,000 particles, it gets extremely messy and almost impossible to solve problems with a high number of particles. Later, physicists such as Maupertuis, Euler, and Lagrange worked toward creating Lagrangian mechanics, which uses energy, which is a scalar, instead of forces. Scalars are better to use because they are inherently less messy than vectors. You don't have multiple coordinates you need to use, and you can use something called generalized coordinates, which make like analyzing physical systems a lot less complicated. So basically, moral of the story is vectors are evil and scalars are good. So why do we need the Lagrangian? The Lagrangian is important because it has the freedom to choose coordinates, which can simplify physics problems. It also eliminates constraint forces and makes the mathematics easier, so tension and normal force completely disappear. The same method is going to work if you have 1 or 20 objects, or 1,000 objects, or 2 billion objects. It doesn't matter. And it scales a lot better than F equals ma. Because if you have F equals ma and you wanted it with 20 objects, it's going to be a lot more complicated than using the Lagrangian with 20 objects. And the cool part is you can confirm that the Lagrangian and Newtonian mechanics both give the exact same answers for the same problems. It just might be a lot simpler to solve it using the Lagrangian. Sometimes it can be simpler to solve it using Newtonian mechanics. It just depends on the problem. But most of the time, Lagrangian mechanics is a lot less messy and way more convenient. And so last but not least, what do you need to start? You're going to need calculus. Derivatives, partial derivatives, integrals. I would say basic integrals, but we're going to be doing some pretty complicated integrals. So if you don't know, like Feynman's trick, elliptic integrals, stuff like that, you might not know how to get through all of the problems. Classical mechanics, you're going to need to know Newton's laws, kinetic and potential energy. Super easy. Basically just physics 1. That's all you need to know. Linear algebra, you only need to know about vectors a little bit because sometimes drawing out vectors or free body diagrams can actually help you understanding how a system works because vectors are a lot more intuitive than energy. And then differential equations, you're not going to need them immediately, but eventually once you see how Lagrangian mechanics works, you can actually derive the equations of motion for a system using differential equations. And almost a lot of the problems in Lagrangian mechanics are nonlinear systems of differential equations. And I will be showing you how to solve those later on, so it will be nice if you start learning now how to solve basic differential equations so you can follow along later. And yeah, that's all for now. Next video I'm going to derive the Lagrangian, and we'll go from there. Thank you for watching.